Hi, everyone. My name is Tai-Yueh Li, and I'm happy to share the result of my participation in the NCHC Open Hackathon in Taiwan last year. And before introducing quantum support vector machine, let's start explain the support vector machine, also known as QSVM. In binary classification text, SVM is a supervised machine learning algorithm. SVM aims to find a hyperplane that separates two datasets. As shown in this figure, in linearly separable data, SVM can easily find a line in the input data space that separate the data of class 1 and class 2. In more complex data set, like nonlinearly separable data, SVM requires a kernel function to map input data into a high-dimensional feature space in order to find a hyperplane that separates two distinct data sets. As shown in this figure, SVM cannot find a linear hyperplane to separate the dataset in two-dimensional input dataset, but with the kernel function transformation, SVM can find a hyperplane in the high-dimensional feature space. And currently, kernel functions are extensively used in many binary classification problems. However, when faced the more complex classification problems, the accuracy of the kernel function is limited. So the quantum enhanced support vector machine, QSVM, is a classical quantum hybrid algorithm. As shown in the figure, the QSVM algorithm uses the quantum feature map circuit to map classical data into the quantum hyperspace, also referred to as the quantum feature space. Due to quantum property, the quantum feature space offers a higher dimensional and more complex data representation capability compared with the classical kernel functions. Current research shows that in specific dataset, the QSVM algorithm outperforms the QSVM algorithm. However, due to the limit quantum bit scale and noise interference in current real quantum computer, the dataset highlighting QSVM's quantum advantage, mainly small-scale point problems, and lead to participability. A great solution to extend QSVM application is to utilize the cuQuantum SDK to accelerate GPU simulation of QSVM computation when large-scale quantum computer is not yet native. In the QSVM algorithm, the operation behind the quantum circuit can be viewed as a series of matrix operation. Those matrix operations are well suited for accelerating use GPU parallel computing technology. Therefore, compared to GPU simulation of QSVM offer a significant speed advantage. Furthermore, unlike a noise quantum computer, GPU computation results are not affected by noise. And in addition, NVIDIA has developed the cuQuantum SDK designed for accelerating and optimizing GPU simulation of quantum computing. The cuQuantum SDK can be integrated with a popular quantum computing framework like Qiskit, Tai-Yueh Li, allow users to use it without complex installation process, and the cuQuantum SDK completes the QSTEP vector and QTensorNet technology. The QSTEP vector accelerates quantum state vector simulation, and QTensorNet utilize tensor network construction to reduce the memory resource need for quantum circuit simulation. In last year's NCHC Hackathon, we applied the QSVM algorithm to real tumor metastasis data and accelerate the GPU simulation of the QSVM algorithm use the cuQuantum SDK. Tumor metastasis is a complex process. Here, genetic mutation enable the primary tumor to spread through the bloodstream and the lymphatic system to other part of body, resulting in a high cancer mortality rate. As tumor metastasis is associated with genetic mutations, utilize the next generation sequence NGS to analyze the genetic sequence of the non-metastatic and the metastatic tumor has the potential to serve as a biomarker for predict tumor metastasis. And we select the clean cell, render cell, sequenoma CCRCC for dataset in our project. CCRCC is the most common RCC subtype, which account for more than 70% of patients with kidney cancer. The dataset and prototype information are freely available with the UCSC database. And the raw dataset consists of the 500 0.9 tumor metastasis and the tumor metastasis data, with each record contraining over 1,000 genetic features. There is a data processing process. First, the raw data undergo a pre-processing step to select 48 genetic sequence highly correlate with tumor metastasis. Then the data is normalized and subject to trend test data split and use the principal component analysis PCA to reduce the feature. Finally, the data will input into the QSVM algorithm. Here is the workflow of the QSVM. The simplified example consists of two data points, X1 and X2. Each have two features, feature 1 and feature 2, as shows here. Those two data points are paired and fit into the quantum feature circuit. Here, the feature of the X1 are embedded into the U gate, and the feature X2 are embedded to the U dagger gate. Each feature corresponds to a qubit. So there are n qubit responding to n features. After the computation in the quantum feature circuit, we obey a correlation A between X1 and X2 in the quantum feature space. Then by repeatedly computing the correlation X1, X2, X1, X1, and X2, X1, and X2, X2 in the quantum feature space, we can derive the quantum kernel matrix. Finally, the quantum kernel matrix is input into the QSVM classifier for classification. So the computational cost of the quantum of the QSVM algorithm consists of two main components. One is the first one is the first component is involved computing the quantum feature circuit with n qubits. This computation cost represent as a 2 to power of n due to the qubit superposition property. And the second component is internal routing 0.5 times n squared is for pair of data calculations. In our case, we require the maximum 48 qubit and need to perform calculation of 334 data points. And our solution strategy in this project. First, we solve the issue of the slow computation speed in the synchronization problem. Before correction, QSVM took as long as 60,000 seconds to compute on CPU for 12 qubit and 350 data points. After correction, the computation time reduced to approximately 250 seconds. And the second, we accelerating QSVM computation use a bootstrap vector. QSVM bootstrap vector bring a significant speed up to our calculation. But we have a memory issue when dealing with the 31 qubit and the 2 data points. And the next we use the cuTensorNet to accelerate QSVM computation, address the issue of the memory issue. And we finished. Unfortunately, although we finished the cuTensorNet program, but we didn't have enough time for comprehensive testing. Here is our result. The result is from the bootstrap vector. In the case of the 31 qubit with 2 data points, the computation time for CPU, A6000 GPU and 800 GPU is 35.8, 1.9, and 1.1 minutes respectively. And 8000 GPU has approximately 19 times faster than CPU. And the 800 GPU has about 33 times faster. In the case of 23 qubit and 344 data points, the computation time for CPU A6000 GPU and 800 GPU were 34.1 minutes and 21.7 minutes and 3 minutes. The 8000 GPU was approximately 1 times faster and then CPU, and the 800 GPU was 11 times faster than GPU. And we also compare the accuracy of two type of QSVM quantum feature map circuit and QSVM on traditional kernel function on chain-link dataset as the numbers of feature changing. So we obey that the QSVM demonstrate a more stable and faster convergence in classification training dataset compared to classical SVM algorithms. And this is our future work. And we will use TensorNet for future to optimization and conduct comprehensive testing. And we want to understand the relationship and the limitation of the dataset, circuit depth, and qubit number on QSVM. And next, we will extend in the QSVM algorithm with even more extensive application. And I will thanks to my finally I will thanks to my team members of Hackathon, Professor Jiale Wu, Professor Fang Chenshu, Professor Yu Zhongxin, and Chen Guanchen. And I also want to thanks for our mentor who assisted us due to the Hackathon, Leo and Jay from NVIDIA. And thanks. This is my presentation.